In section 3, and for that matter in section 4, we're going to be talking about sampling. And again, we're kind of jumping to a new topic. We've said that a sample is a subset of the population. What we're going to generally want to do in statistics, because it's not generally going to be practical to get information from every individual in the population, we're going to have to use a sampling process. So in order to get a sample that is most likely to represent the population, we're going to use randomness. Random sampling is the process of using chance to select individuals from the population to be included in the sample. So if we use random sampling, we're using a scenario where every individual from the population has a random chance of being picked to be a part of the sample. That is random sampling. Now, if we have a scenario where not every individual of a population has a chance of being part of the sample, then that sample is going to be suspect. In other words, the results that we obtain from that sample is going to be less likely to represent the population than if randomness is used. So the key to obtaining a sample that represents the population is to let chance or randomness play a role in dictating which individuals are included in the sample, rather than convenience. If convenience is used to obtain a sample, the results of the sample are not statistically meaningful. We'll learn more and more and more about what that means to be statistically meaningful as we go through this course. So there are really 4 main types of random sampling that we're going to be looking at. And if we're doing a statistical study and we're going to be selecting a sample, usually one of these 4 types of random sampling is used, or a combination of these 4 types are used. The first method is called simple random sampling. So let's say we have 11 people in this class. So suppose I wanted to randomly pick 3 of the 11 of you. So you're my population. There's 11 of you, and I want to randomly pick 3. How could I do that? So I could put your 11 names in a hat, I could shuffle them up, and I could randomly draw out 3 of you. So I reach in and draw out 3, and so that would give me a somewhat random sample. So every individual in the population has a chance of being included in the sample if I draw names out of a hat, for example. Now, the first sampling type that we're going to talk about is called simple random sampling. And the definition I'm going to speak is a little bit different from the definition that's written down here. First thing that I want to mention, the letter capital N. The letter capital N is our first statistical notation that we're going to use in this class. Capital N is always going to represent the population size. So for our class, capital N equals 11, because there's 11 of you in my population of students for this class. Lowercase n is going to represent the sample size. So from now on, as we go through this course, capital N always represents the size of the population. Lowercase n is always going to represent the size of the sample. So in my example, capital N equals 11 because there's 11 of you. Lowercase n equals 3 because I'm going to pick 3 of you. Now, to be a simple random sample, every individual in the population has to have an equal chance of being picked to be in the sample. Let me say that again. Every individual in the population has to have an equal chance of being included in the sample. So no one of you is more or less likely than any of the other of you to be picked to be in the sample. Everyone has an equal chance. If that's the case, then that is a simple random sample. So if I put the names in a hat and draw out 3 names, it would be somewhat questionable whether or not everyone had a truly equal chance of being picked. So in order for everyone to have an equal chance, let's say I'm writing your names on a piece of paper, all of those pieces of paper would have to look the same, feel the same, be the exact same size, the exact same weight. They would have to all be identical in order for everyone to have a truly equal chance of being picked. And when I shuffle them up, I would have to make sure that there's no names that are getting stuck in the bottom of the hat or anything like that, so that some individual has a greater chance than the others of being picked. So executing a simple random sample isn't really all that simple. It's actually somewhat complicated to actually construct that. A good example of simple random sampling is like if you've ever watched the lottery, like the lottery drawing with Powerballs and those kinds of things. You've seen the balls get shuffled around in a lottery drawing and then they pop up. Those are very meticulously made so that all of those balls weigh the exact same, so that one doesn't have a higher chance of being picked as a winning number than the others. It's very complex to do, sophisticated. So take a look at this definition. So this definition says a simple random sample of size n, so again, that's our sample size, from a population of size capital N, so that's our population size, is obtained through simple random sampling if every possible sample of size n has an equally likely chance of occurring. The sample is then called a simple random sample. Now, does that definition say what I said? It's not exactly what I said, is it? What I said is every individual in the population has to have an equal chance of being picked to be in the sample. And that's true. But this definition doesn't say that. This definition says that every sample of size lowercase n has to be equally likely. So out of my population of capital N, every sample of size lowercase n has to be equally likely. Now, what exactly does that mean? Well, use our example. For our example, I'm going to write up here at the top, capital N equals 11 and lowercase n equals 3. So how many different samples would be possible? How many samples of size 3 would be possible? Now, I will show you how to figure this out later on, but there would be 165 different samples that are possible. So altogether, if we have 11 individuals in our population and we're picking samples of size 3, there would be 165 samples possible. And so what this definition is saying is that all 165 of those samples have to have an equally likely chance of occurring. So pretty much it means the same thing, that every individual has an equal chance of being picked. So take a look at our example here. Faye needs to choose 3 roommates from a group of 5 friends who have expressed interest. Anna, Betty, Cindy, Darla, and Ellie, those are the friends. Faye decides to randomly select the 3. List all possible samples of size n equals 3 from the population of uppercase N equals 5. So in this example, we're going to list all of the possible samples that can occur. So Faye is picking 3 out of Anna, Betty, Cindy, Darla, and Ellie. Now, when I made this example, I used A, B, C, D, E for the first names just so I can reference them by their first initial rather than having to write out the whole name. So what we're going to do again is we're going to list all of the possible samples of size 3 out of this sample of size 5. So it's possible that my sample could consist of Anna, Betty, and Cindy. That's one possibility. It's possible we could have Anna, Betty, and Darla. And it's possible we could have Anna, Betty, and Ellie. So there's three examples, or three samples where Anna and Betty are both in the sample. Now it could also be, instead of Betty, we could have Cindy. So we could have Anna, Cindy, and Darla, or we could have Anna, Cindy, and Ellie. Now I didn't say Anna, Cindy, and Betty because Anna, Cindy, and Betty is already up here. It's also possible we could have Anna, Darla, and Ellie. So these are all of the possible samples where Anna's involved. So again, Anna, Betty, Cindy, Anna, Betty, Darla, Anna, Betty, Ellie, Anna, Cindy, Darla, Annie, Cindy, Ellie, and Annie, Darla, Ellie. Now there are still other samples possible though. These all involve Anna, but there can be some samples where Anna's not involved. So for example, we could have Betty, Cindy, and Darla. That's a different sample. We could have Betty, Cindy, and Ellie. That's a different sample. And we could have Betty, Darla, and Ellie. That's a different sample. Now I have accounted for all of the samples that Betty can be in. She can be in these three, and then she can also be in these three. In addition, we could have a sample that consists of Cindy, Darla, and Ellie. So altogether, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 different samples that are possible that Faye could end up with. So if Faye is going to randomly choose her roommates, then each of these 10 outcomes have to be equally possible if it's going to be a simple random sample. So again, if it's a simple random sample, each one of these 10 different samples has to have an equally likely chance of occurring. So how do we actually go about determining the simple random sample? Well, the first thing we have to do is we have to find a frame for the population if we're going to use simple random sampling. So that means that we have to have a list of every individual in the population. So we obtain a frame of the population, which is a list of all the individuals within the population. That is probably the most difficult part of simple random sampling, obtaining the frame. If we have a relatively small population, then obtaining a frame is probably not going to be that big of a deal. So like if you guys are my population, well, that's very easy for me to obtain a frame. I have your name, so I can obtain a frame very easily. But if I have a population of 1 million individuals, now obtaining the frame is going to be a whole lot more challenging. And so that is one of the limits, I guess, of simple random sampling. The next thing we can do is we number the individuals in the population from 1 to n, where n is the population size. Randomly select n distinct numbers from this list where n represents the size of the sample. So a random number table or technology such as a TI graphing calculator or StatCrunch can help when finding a simple random sample. So I'm going to look at an example where we can determine a simple random sample. And so first we're going to use a random number table. And then after we have the random number table example, after we do that, I'm going to show you how to do it with technology as well. So here's our example. The following table lists the 45 presidents of the United States. Use the random number table shown below, and this is table 1 from the appendix of the textbook, which is on page A-1, A for the appendix, and it's page 1 of the appendix. to obtain a simple random sample of size 6. So here we have our individuals in our population. We have a relatively small population. Again, it's 45 individuals. Now, I will point out that number 22 and number 24 are the same individual, Grover Cleveland. Grover Cleveland's the only president who was, to this point, elected to be president in non-consecutive terms. So he's considered president number 22 and president number 24 for that reason. Now, when they're elected consecutively, like for example, like Bill Clinton, for example, had consecutive terms, so he only gets one number. George W. Bush and Obama, they each get only one number because they were elected to consecutive terms. Anyway, so we have a population of 45. You could argue that it's really only 44 since Grover Cleveland was the same individual, but he's generally historically counted as 2 individuals. So we're supposed to obtain a simple random sample of size 6. So we're going to randomly select 6 of these presidents. And again, if we end up with Grover Cleveland twice, we end up with him twice. I suppose we could deal with that if that happens. Okay, so anyway, we have a frame of our population. We already have them listed and we have them numbered by the number of president that they were. So how do I go about using a random number table or technology to randomly select my 6 individuals to go in my sample? So again, first of all, I'm going to use this table. This is a random number table. Again, this is in the appendix of your textbook, so you can get a copy of this from the appendix of your textbook, or obviously I've included it here on your note sheet as well, so you can have a copy of it from that. Now, this is called a random number table because these numbers have no real meaning. They were just randomly assigned in this table. And when I say randomly, I mean like literally like this was probably generated with a computer program, but it's as if they had like the numbers 0 through 9 in a hat and they randomly drew out a number and it happened to be 8. And then they drew out another number, it was 9, and then 3, then 9 again, then 2, and so on and so on and so on. So there's no meaning to these numbers, they were just randomly assigned. Anyway, so this table is now organized into rows, which are this way, and columns, which are this way. So this number 8 right here is in the first row, first column. The number 9 right there is in the first row, second column. The 3 is the first row, third column. The 9 is the first row, fourth column, and so on and so on and so on. There's no meaning to the spaces between the columns. The only reason they put those spaces there is to just try to help you kind of keep it straight. If they were all glommed together, it would be hard to tell one column from another as you go down the column. Anyway, so if I'm going to randomly select 6 individuals from my population, so the first thing we've done is we've numbered them. They're numbered from 1 to 45. So I'm going to select a starting point in my table, and I'm going to look at 2-digit numbers from 1 to 45. Now, when I say 2-digit numbers from 1 to 45, you might say, wait a second, 1's not a 2-digit number. So what we're going to think of when we think of the number 1, since we need a 2-digit number, we're going to think of that as the number 01. So 01 is a 2-digit number representing 1. 02 is a 2-digit number representing 2, and so on. So just for simplicity for our first example here, I'm going to start in the top left corner here, and I'm going to look at 2-digit numbers, and I'm going to proceed down until I get 6 presidents. So my first number is 89. Now, the trouble with 89 is we didn't have 89 presidents. We only go up to 45. So when I get a number that's outside of my number range, I'm just going to skip that. So I'm going to skip 89. I'm going downward, so the next thing is going to be 61. Well, we also don't have a 61 in our population, so I'm going to skip it. The next is 11. So President 11 is going to be the first president in my sample. So that would be Polk. So Polk's going to be one of my 6. Next is 27. 27 is Taft. So Taft would be in my sample. Next is 36. 36 is LBJ. So LBJ is going to be in our sample. Next is 81, which I have to skip. Next is 59, which I have to skip. 46, I have to skip. 24 is Cleveland. So Cleveland is my 4th individual. 98, we skip. 14, Pierce. He's our 5th. 55, we skip. 96, we skip. 38 is Ford. So Ford would be our last president in our sample of 6. So we had 11, 27, 36, 24, 14, and 38. Those are the numbers of the individuals. So again, that would be Polk, Taft, LBJ, Grover Cleveland, Pierce, and Ford. Those would be the 6 presidents that make up my sample. Now, I do want to make a statement about using a random number table. One problem with a random number table is if I use the same procedure each time, then I'm going to always get the same sample over and over and over again. So like, for example, if I come in on a Wednesday and I say, hey, let's pick 6 presidents out of our population of 45 presidents. And if I start with this top left corner and I proceed down, I'm going to get the exact same sample that I got today. So the problem with the random number table is that once the numbers are printed in a table, they're no longer random. They're no longer random. If I use the same process, then I'm always going to get the same results. So that's an issue. So if we're going to use a random number table, then what we have to do is change up our process. We can't use the same process every time. So I can't always start in the top left corner. So in reality, what I probably should do instead of starting in the top left corner is I should maybe like drop my pen on the table, and wherever it points, that's going to be where I start. So like in this case, if you look at my pen, it was closest to this right here, to this number 26 right here. So now, because I dropped my pen, I am being a little more random in where I'm starting. So if I had done that, then number 26 would be my first individual. And then number 95, which I'd have to skip, and then 18, then 17, then 65, which I'd skip, and so on and so on and so on. Actually, let's do that, okay? I'm gonna write these down here. So 26 would be my first individual, 95 I skip, 18 would be my second, 17 would be my third, 65 I skip, 82 I skip, 46 I skip, all because they are outside of my range of presidents, okay? Now, when I reach the bottom, I have to have a procedure of how to move forward from there. So typically what I would do is, since this is the bottom of these 2 columns here, I would go to the top and use the next 2 columns. So like, for example, the 4 is in the 16th column and the 6 is in the 17th column. So I would go up, I would have 59 here is in the 18th and 19th columns. So 59, which I'd have to skip, 64 I'd have to skip, 44, that one's okay. 24, that's okay. 84 and 9. So in my second sample, I would end up with number 26, number 18, 17, 44, 24, and 9. So my sample would be 26. That would be Theodore Roosevelt. 18 would be Grant. 17 would be Andrew Johnson. 44 would be Obama. 24 would be Cleveland again. And number 9 would be Harrison. And so actually that's William Henry Harrison as opposed to Benjamin Harrison. So those would be the individuals in my sample. My point is, with looking at that one, is you have to have a procedure of what happens when you get to the bottom of the column. How are you going to proceed? And again, I don't have to always proceed downward. I could proceed to the right. So I could have started with 26, and then I could have gone to the right, 52, and then gone to the right, 58, 36, 47, 31, 98, and so on. I just want to change that up so that I'm not always doing the same thing.